All right, we are wrapping up this unit with log applications, aka word problems. So on these first three, we are going to be solving exponential equations, which of course you have to use a log for when they are not perfect numbers, and none of these are. So starting with the first one, I've got the population of a town currently. We're going to pretend that it's still 2024. We have a population of 8,250. If it has been increasing by 3% each year, and what year was the population 7,000? Well, in order to solve this, I first need to write my equation function for my population. I'm going to call that P of t, my population depending on time. To write that equation, I'm going to take our starting population, and then I'm going to take 1 plus our percent of increase. 3% as a decimal is 0.03, and that's to the t power. And the reason I'm adding these is because I want exponential growth. I want this value, that's the base of our exponent, to be greater than 1. So this is my function. In order to find when the population was 7,000, I'm going to set this equal to 7,000 and solve for t, time. So in order to do that, I first need to isolate my base, 1.03. So that means I need to divide 8,250 on both sides. This will not divide evenly, so I'm going to keep it as a fraction. Now that my base is alone, I can rewrite this in log form, and that will be log base 1.03 of 7,000 over 8,250 equals t. This is where my calculator comes in. And t is approximately negative 5.559 years. Now, why is this a negative value if we're talking about time? Well, if our population has been growing, to find a time when it was less than it currently is, that means we're going to have to go into the past, back in time, about 5.5 years. So if we're saying present day is 2024, this is going to be sometime between 2018 and 2019 when that occurred. Okay, moving on, I purchased a car for $16,000 in 2012, and it's depreciating at a rate of 7% annually. In how many years will it be worth $5,000? Well, first I need to again write the exponential decay equation for this one because we're depreciating. I'm going to call that V of t, the value of my car. So it had a starting initial value of 16,000. And this time I'm going to do 1 minus my depreciation rate because with this being decay, I want the base of my exponent to be a number less than 1, and it is 0.93. So to find when the value of the car will be $5,000, I'm going to set this equation equal to 5,000. And I want to get my base alone, so I will first divide by 16,000. Again, this will not divide evenly, but I can simplify. We have 3 zeros on the top and the bottom, so this reduces to 5 over 16. Okay, now that that's alone, I can rewrite this in log form. That will be log base 0.93 of 5 over 16 is equal to t. This is where we get the calculator again. And t is approximately 16 years. So 16 years, if I bought it in 2012, will be sometime approximately in 2028. All right, last one, if I'm investing $10,000 in an account with 4.5% interest, how long will it take for me to double my investment? Well, this is going to be another exponential growth function, hopefully if it's a good investment. So I'm going to call it I of t, my investment. I'm starting with 10,000. And I'm going to add my interest rate because I want exponential growth. I want my base to be larger than 1. Okay, to find when it's doubled, that means that my account, 20,000. So following similar steps we did on the previous 2 problems, I'm first going to divide. To get my base alone, this will divide evenly down to 2. So in log form, this will be log base 1.045 of 2. This is going to give us our time. This is where we have to get our calculator out. And we have about 15.747 years, which is like your whole lifetime. Okay, moving on to the back, this is going to be a little different, but I promise it's not too difficult. What we are going to explore is the Richter scale and earthquakes. And I'm not going to read through this whole thing because it's quite wordy, but essentially Charles Richter, invented the Richter scale, and this formula is what we use to calculate magnitude of earthquakes. So the magnitude is log, again, if there's no base written here, we're going to assume it's 10, of I over S, where I is the intensity of the earthquake that's being measured, and S is the standard intensity of what is normally being felt. So even under your feet right now, tectonic plates are shifting. There is intensity, but you don't feel it because it's so minuscule, so we call that the standard. So what we're comparing is the intensity of an earthquake we can measure to the standard, and that is what goes into your log to calculate magnitude. So what would the magnitude be of a standard earthquake, which has an intensity of S? So what that's saying is I is equal to S. So if I put that into my magnitude formula, I would have the log of S over S. Well, S divided by S is 1. So if I want the log of 1, that means I'm saying 10 to some exponent is 1. Well, that would be to the 0 power. So log of 1 is 0, which means the magnitude for a standard earthquake is 0. All right, now the largest earthquake ever measured was this earthquake that happened in Chile in 1960, and it had intensity 3.2 billion times more powerful than the standard intensity, or 3.2 billion S. So that is 32 with 8 zeros behind it. What is the magnitude of this earthquake? Well, we are going to put that into our magnitude formula. This is telling me that I is equal to this value, so 32 with 8 zeros S over S. Again, S divided by S is 1. So we're looking at the log of 3.2 billion. And this is where I would get the calculator involved. I can just use the one on the home page since it has a base of 10. Making sure I get all those zeros in there so I can get the correct magnitude, which is approximately 9.5. Okay, how much more powerful is a magnitude 6 earthquake than a magnitude 5 earthquake? Well, if we're thinking about how we measure magnitude, right? So if I have a magnitude of 5, that would mean I had the log of the intensity for a magnitude 5 over S. And if I had a magnitude 6 earthquake, that would be log of intensity 6 over standard. So if I'm looking at both of these, what this is saying is here, this is saying 10 to the 5th is equal to that intensity over the standard intensity. And this is saying 10 to the 6th is equal to that intensity over the standard intensity. So what is the difference here? Well, 10 on an order of 1, or 10 to the 1st power. So it is 10 times more powerful. So if I then go on to consider a magnitude 8 earthquake versus a magnitude 5 earthquake, that means I'm comparing 10 to the 8th and 10 to the 5th, which has a difference of 10 to the 3rd, which is equal to 1,000. So that's a difference of 1,000 times more powerful. Okay, so on that note, how much does the intensity of an earthquake increase every time it goes up in magnitude? Well, by 10 times. Every time we're going up in magnitude, we're going up by an order of 10. Okay, so the last part we're going to look at is this historic San Francisco earthquake, which is quite destructive, but it was not as severe as the one that happened in Chile. The one in Chile was 50 times more powerful. So if I want to determine the magnitude of this earthquake, what I'm going to need is the intensity for the San Francisco earthquake. And if the one in Chile was 50 times as powerful, that means I can take the one from Chile, that 3.2 billion S, and divide it by 50. And what that will give me is 64 million. So that's 6 zeros S. So to calculate that magnitude, I'm going to take 64 million S over S, and that should be inside of a log, I apologize. So again, those S's divide to 0, so I need to find the log of 64 million. Handy dandy calculator. And I got 7.8 as the magnitude of that earthquake. All right, that wraps up our word problems, our applications with logarithms.